Here are a few problems from Chapter 20 involving Ohm's law and the power law. So problem 7, defibrillator, and I think you can read through this. So there's 10,000 volts on here, and there's a 6 amp current going through here, and what is the resistance? And it's just Ohm's law that is involved, and then there's a follow-up, how much power. And so I wrote Ohm's law down here again. These are the three forms that it comes in. I only have one of them memorized, R equals V over I, resistance equals voltage over electric current, and the capital I stands for intensity of electric current. And then, of course, one algebra step, and you get the other two forms. Current equals voltage over resistance, or voltage equals resistance times current. As I said, I only have one of them memorized, and I just use one algebra step to get to the others. Similar when I talk about the power law in a minute or so. So let's see. Just here's the calculation, and I can show you that on the calculator. So here we go. It says 10,000 divided by 6. So 10,000 divided by 6. And then, of course, here, and then round, and I guess they didn't tell us how many sig fig they had on the 10,000. So 3 on the 6.00 amps, so 1,670 kilo ohms. I wouldn't write it as 1.67 kilo ohms. I would write it as 1,670 ohms. And I will show that in a moment here with the PHET, Physics Educational Technology Circuit, the applet that is free on the internet. And then there's a follow-up question. So the defibrillator pedals make contact with the patient through a conducting gel that greatly reduces the path resistance. Discuss the difficulties that would ensue if a larger voltage were used to produce the same current to the patient, but with the path perhaps 50 times the resistance. And the answer to that, this is actually from the solution manual, that would be the answer to that. You could get a serious burn if you didn't use that gel, because then you would have to really increase the voltage, increase the current, and yeah, you get a burn on the skin. This one here, I wrote this. This is using the power law. It says use this equation for the power. It comes originally from, let's see, I wrote it right here. Power equals electric current times voltage. Again, that's the only one that I have memorized. There are two alternative ways to look at it when you apply Ohm's law to that. So current equals voltage divided by resistance. You get this one here. Power equals voltage squared divided by a resistance. Or if you say, okay, voltage equals resistance times current and plug it in here, then you get this one here. Power equals current squared times voltage. So these three forms for the power law, again, I only have one of them memorized, this one right here, and then I just use Ohm's law, plug it in, or maybe I do two steps. So I really don't have them all memorized. There is, by the way, I found a pretty good website, so let me go there. This is the circuits here. I mean, there are plenty of good websites. So I found this one here, how to use Ohm's law, and you will find this triangle in some textbooks. Turns out I've never seen it in a physics textbook, actually. And again, I don't really need that triangle because I just have one form memorized, R equals V over I, and then even without the triangle, I know what the algebra is. But, you know, you could use that. Here's something else where they say that, okay, voltage equals current times resistance. Can you see that? Or current equals voltage divided by resistance. By the way, here the capital E stands for electric potential, which is the same as voltage, not to be confused with energy. I get that actually in a minute here. So usually the two don't show up together. I prefer V for voltage. And then here's the third form. And then they write it down here again, and here's a circuit and so on. And then they get to the power law. Here's similar for the power law in the original one. And then they put it all together, and whoa, you have this big power wheel, I think I call it here. There should be a capital V, that would be pretty cool. Capital V all the way through here, and you recognize certain forms of these depending on what you're solving for. But then again, I have nothing of this memorized except just two forms. Let's see, right here, power equals voltage times current, and the other one is, where to go, there it is, resistance equals voltage divided by current, and everything else derives from that with 1 or 2 algebra steps. So anyway, wanted to point that out. All right, let's go back to the problem here. So plugging in numbers, what is the power here? Oh, I think they don't even do that. They just say, well, how much more is it? And you would have to use this form here. All right, let's go to the next one. So again, a defibrillator to bring a patient out of cardiac arrest. That is the question that I want to ask someone in paramedics or so. Because look at this. For this particular defibrillator, it is 5 volts. For the other one, it was 10,000 volts. Well, this one is the one that you stick to the chest as you're used to it. But look at this. This one here is open heart surgery. So do you put that tiny defibrillator, which has much less voltage, directly onto the heart? I'm guessing yes, but that would be a question for them. Okay, anyway, 500 ohm resistance, 10 milliamp current. So to figure out the voltage is current times resistance. So I'm going to plug in these numbers, 500 ohms times 10 milliamps, which I'm going to write as 0.001. Oops, and then I made a mistake, right? 0.010, 10 milliamps, that is. So it's 0.01 amps. Enter, and obviously I come up with 5 volts. I have both of these problems here using the Fet Circuit. This one here was the first one with the defibrillator, and I think it said, let me see, 10,000 ohms. The battery here, it doesn't allow me to go all the way to 10,000 ohms. So I'm sorry, 10,000 volts. So I just used 10 volts here. And then it said the current ought to measure, what does it say again? 6 amps. So I'm going to put that there. There's nothing measured yet because the switch is open. Close the switch. And so this is supposed to read 6 amps. So I'm going to increase this one here. Or I'm going to change the resistance until it says so. And then, again, it doesn't allow me much leeway here. Here, this must be, this is going to cut it. Yes, it does say 0.6 amps in there. And this one here, the result is 1,670 ohms. But notice the slider here doesn't allow me to go even that high. So I just chose 16.7 ohms. And then compared to, oh God, this is really a little long here. And then this one here says 0.6 amps, while the original one said 6 amps. So I'll shift the decimal point here with the Fet Circuit. All right, this one is the other one, the one with the second defibrillator. So I put 5 volts here. This one here should be 500 ohms, but I'm not going to get it to 500 ohms, so I'm just going to push it to 50 ohms. So again, shift the decimal point, close the switch, and then put the no contact ammeter in here, which works with the Hall effect, measuring the magnetic field through a wire and calculating therefore the current. So this one here says 0.1 amps, and the problem said it's actually 0.01 amps or 10 milliamps. So again, shift the decimal point, and yeah, that's basically it on there. A couple of things to point out here. Notice the electrons are flowing here. Of course, the larger the current is, the faster they're flowing. And then there's another label here that says conventional. So I'm going to click on it, and now it says that the current goes in the opposite direction. This is from the 19th century, before the electron was discovered, and in the 18th century, when Lichtenberg and Benjamin Franklin, actually, so Georg Christoph Lichtenberg and Benjamin Franklin came up with a definition of what is positive and what is negative in electricity. And they made an arbitrary decision and says, hey, this is positive, this is negative. And I have a blurb somewhere in my course where you can actually read that, how they came up with that. And it still turns out, hey, it's arbitrary. So then physicists decided, hey, we're going to have the current go from positive to negative. And this one here is the positive side of the battery, and this is the negative side here. So it goes positive. Then in 1900, actually, Thomson, J.J. Thomson, I think, discovered the electron, which is negatively charged by the definition. And it's the electron that is flowing the other direction. So ever since we have this arbitrary definition of positive and negative, and one flows in the other direction, but it's actually the electrons that are flowing, and we're kind of stuck with it. And you see that in all kinds of physics and electrical engineering textbooks, and we always point that out. Yes, the conventional current flows in the other direction, but it's the electrons that flow in that direction, and we know it, but it really is not all that important. All right, the third one here, by the way, is the flashlight. So let's see, it says in here 3 volts. So I'm going to adjust this one here to 3 volts. And that takes a little while here. There we go, 3 volts. And then it says that this one here, the lamp is actually, 3.6 ohms. I have to get it all the way down here. I'm trying to grab it. Whoa. Okay. There we go. And then I'm going to close this one here, and there's the lamp, and then it measures 0.83 amps. And then I'm going to go back here, which of course is the answer right in front of us. So that would be the next problem, something about a flashlight, 3 volts, 3.60 ohms. And so 3 divided by 3.6 is the answer, 0.833 amps. And now I used Ohm's law in all 3 ways that it comes at, one algebra step away. So I equals V over R, V equals I times R, and I equals V over R. Or did I use that twice? Oh, I did. No. R equals V over I, right there. There it is. So I used it in all 3 forms. All right, let's see. One little thing I left out here as I introduced the power equation right here. So in electricity, it's power equals electric current times voltage. We have seen it before in the energy chapter. So power is energy divided by time, how fast you use up the energy. And notice the capital E right here means energy. Earlier it was the same E, but it meant something else. It was the electric potential. Respectively, this one here, power equals force times velocity. Whenever I see that equation, I'm thinking of a bicycle, that you put this much force into pedaling, and your bicycle is going at a certain velocity. And of course, putting that much force into pedaling overcomes the friction and air resistance that you have. And so force times velocity is the power on a bicycle, or for any kind of thing that you're using. Respectively, when you shift gears in the bicycle, you actually notice that all of a sudden you have to use a large force, going uphill. You shift it into a lower gear, but of course then you have small velocity, or if you're coasting along, then you put it into a higher gear and you have a large velocity, but only a small force. So these are the original power equations that we saw before. Here, the power, this is the same thing. It's measured in watts. Watts has a really strange unit there. You can see it, kilograms meters squared per second cubed. But this is the one that we would use in electricity. Okay, I'm going to give myself a break before I move ahead with the next one. All right, so something about a generator at the Hoover Dam, and it says it produces a current of 8,000 amps at 250,000 volts. What is the power output? So all I have to do is plug it in here. P equals I times V. And obviously when I plug that in, I will come up with the same answer that I copied from the solution manual. So this one is 8,000 times 250,000. 1, 2, 3. There we go. And I come up, and if we count the zeros, I guess 3, 3, 3. Yes, 2 billion watts. Then the follow-up question is the water that powers the generators and so on, but loses 160 meters in altitude. How many cubic meters per second are needed, assuming 85% efficiency? Whoa, that sounds complicated, but they break it down for us. We'll start out with the potential energy, and then we introduce, well, we don't actually have potential energy here. What we have in here is the power. So they divide right away by 1 second. You see here how many cubic meters per second are needed? So right here on the next line, divide that by 1 second. So PE divided by 1 second, energy divided by time, is the power, which means that is actually the 2 billion joules. And that is then divided here by the mg from the potential energy equation, so divide by gravity and divide by height. So I'm going to take the 2 billion here, and I divide it by the 9.80, and I divide it by the height. It's at 160 meters, which is about 500 feet, a little bit more. That's how high the Hoover Dam is. Hit enter, and obviously I come up with the same number that they come up with here, which is 1,276,000 kilograms per second. So that's the mass that flows through. And then it actually asks for how much volume of water. Well, there's exactly 1,000 kilograms in 1 cubic meter of water, because the density is 1,000 kilograms per cubic meter. So divide this one here by 1,000. There we go. And that's the 1,276 cubic meters that is going through every second. And if I convert that to American units, let me do that for just a moment. Okay. About 3 feet, actually 3.3 feet to the meter, but I would have to cube that, so 3.3 cubed is in the neighborhood of, I think, like 30 or something. So I have to multiply that by 30, so approximately 40,000 cubic feet is going through there every second. And then it says something about the efficiency, only 85%, so I divide that by the 0.85. And there we go. So, which is what it says here actually. Oh yeah. So actually 1,500 cubic meters per second, and that one I multiplied by roughly 30 or a little bit more, so about 50,000 cubic feet that is going through to produce that amount of power, the 2 billion watts that we had earlier at 250,000 volts and 8,000 amps. All right, let's see what the next problem is. All right, okay, I'm going to give myself a break here. All right, so here are a few problems from chapter 21, which is on circuit. So here we put resistors together in parallel or in series, or combine parallel and series. So we're going beyond Ohm's law. And I put this little table up here that in series resistance is simply add. In parallel, you add the reciprocals, and for capacitance, as we have seen it before in, I believe, chapter 19, it's the other way around. In series, you add the reciprocals, and in parallel, you simply add. But before I start here, I want to review actually chapter 20 here on circuits, at least a little bit. So I'm going to go over there. There we go. And I want to start in section 3 here, Kirchhoff's rules. This one is actually a quite complicated circuit, the one that we have in front of us. I deal with that in a different kind of recording here for the homework. So let me go on. Kirchhoff's rules themselves are actually really easy, and there are only 2 of them. So here is the first one. Basically, when you have a junction, then the amount of current flowing into the junction equals the amount of current flowing out of the junction. Makes total sense, right? 11 amps go in, it splits up because it just so happens to be a circuit that branches off. All kinds of circuits do that all the time. So 11 equals 7 plus 4, what we see in front of us. Okay. The other one, this one here, here's the second rule, is just as easy. It actually looks a little bit too complicated for me here. So here, for example, we have a battery of 18 volts, and now these 18 volts of the battery here are distributed in this series circuit. So here, this one here takes 1 volt, then this one over here takes 12 volts. Just calculate 17 minus 5 here is 12. So 1 volt here, 12 volts here, and 5 here. You add the 3, you come up with the original 18 volts. And that is what's called the loop rule, that when you go around, you arrive at the same voltage with which you started out. Again, makes total sense. So one of them, the loop rule for the voltages, and the other one, the junction rule for the electric currents. Okay, now I'm going to go back to the first section here, the resistors in series and parallel. So this is the typical series circuit. This one here would be a parallel circuit. Notice they're parallel with each other. Here they're in series with each other. And then, of course, combinations. And then if you look at any electronic circuit, yes, they have a total combination of these kinds of circuits. And resistors aren't the only ones. You have capacitors in there. you have inductors in there, transistors, and what have you. In a basic physics book, we start out with resistors. Okay, so resistor and series, they actually have a neat derivation here, so they use Ohm's law to simply derive for us the easy one, which is that in series, the resistors simply add up. So if you read through the algebra right here, right in front of us, you will, they actually derive it for us. Hey, this is how we come up with that. And then it all kind of makes sense. The other one for the parallel one, so let me scroll down. This here are all kinds of examples. So here's the parallel one. Here, of course, the surprising result is this one right here. At the reciprocals, and that equals the equivalent resistance also as a reciprocal. Where does that one come from? Well, it also comes from Ohm's law, where here you can see this one here. This is the junction rule, Kirchhoff's junction rule. And so the electric currents, they add up, getting the total current. Then the voltage is the same for each part in a parallel circuit. And you plug in Ohm's law. And then because the voltage is the same, that actually divides out or can be factored out. And what remains then is at the reciprocals. I don't know why there's a dot right there, or is that on my screen? No, that's in the book. So at the reciprocals, and that is 1 over the equivalent resistance. I'm going to give myself a pause because I'm wondering if I want. I think I'm going to talk about this one later. The combinations of series and parallel. So let's go to this one here. So here in this first problem, I kind of like this problem here. Now, what are the largest and smallest resistances you can obtain by connecting a 3650 ohm, 7 ohm resistor together? And so they have this one here and they have this one here. Well, the largest one is you simply put them in series, which is exactly what they do here, right here. 36 plus 50 plus 700 is 786. By the way, this one right here is supposed to be a decimal point. I got that from a solution manual. I cannot fix that. So you come up with the 786. The smallest resistance you can get is if you put them all in parallel. And so if you look at the reciprocal equation here, when you plug in numbers, you will see that as you add positive numbers here as reciprocals, the end result is always smaller than the smallest one that you start with. So then the smallest resistance. Notice that the result is 20.3 ohms compared to the 3650 700. It's smaller than the smallest one, which is the 36. I'm going to show you that in a calculator in just a moment. By the way, I cannot fix that either. I don't like that little dash in there. I would just write 36.0 ohms and leave the dash out because it looks like a minus, which it's not. And then the other odd thing about this problem, as I said, I do like this problem because it's asking for largest, smallest resistance. The other interesting thing it does is it takes 3650 and 700 ohm resistors. Usually what I like to do is I try to put them still different, but in the neighborhood of each other. Notice that when you add 36 and 50 to 700, it's a 700. Of course, the largest resistance that makes the difference, right? There's the 700 in there, and then you just add 86 to it. Not much. And notice that in the other one, well, I'll show you that in a moment. So let's see, calculator. There we go. These are the calculations from earlier. I think I can spare your 36 plus 50 plus 700. So let's do the reciprocal one. There are several ways of doing it. This is my way. You don't have to do it that way. I plug in 36 to the, oops, I don't need that, to the negative power plus 50 to the negative power plus 700 to the negative 1 power. Close the parentheses, and then I need to invert it again. There we go. Enter. And of course, I come up with the 20.3 ohms. There is several other ways you can do it. 1 divided by 36 plus 1 divided by 50 plus 1 divided by 700. Enter. And then 1 divided by the answer. Same result, obviously 20.3. You can use the one that I just showed, or you can use the one that I used earlier. The first one is just more comprehensive and it's quicker for me to use. So 20.3 ohms is the answer. By the way, I mentioned something about that. Well, does the 700 really matter in a parallel circuit? So let me go back to that one. There we go. So notice that the answer would be 20.3, but what if I actually don't have anything there? Ooh, that's not going to work. I didn't mean to do that. I would have to be a really large value. So if I just leave it out, notice I get 20.9 ohms. So the 700 ohm resistor in the parallel circuit really hardly participate, which makes sense. There is that saying, an electric current chooses the path of least resistance. Well, if you already have 700 ohms, then it's going to rather flow through the 36 and the 50 ohms because they have a smaller resistance. Okay, anyway, let me go over to the Fet Circuit, P-H-E-T. I have to find it. Let's see, there it is. And I set up the Sears circuit here. Again, notice the resistances that I use here. I cannot use 700. It doesn't allow me that. So I get to up to 120. So I just chose 70. So I'm off again by a factor of 10. So I have 70 and 5 and 3.6. So the ratios are still the same among them. I'm going to put a switch in here. And I'm going to close the switch here. There we go. And I'm going to put the ammeter here. And the thing is, this particular circuit applet, by the way, I want to show values. Did I show them earlier? I forgot. Anyway, this particular applet doesn't let me know, that doesn't let me measure resistances. So they either give me the values, but I cannot figure out, I cannot measure the equivalent resistance because they only give me a voltmeter and an ammeter. They don't give me an ohm meter. So what I'm going to do is I'm going to increase the battery voltage here until I get a nice 1 amp, and then I'm going to use Ohm's law. Okay, so I'm going to get up to here to, they're really close. There we go, 1 amp. So here I have now 78.2 volts divided by 1 amp. Ohm's law is 78.2 ohms, but because I've shifted decimal point, it's 782 ohms, which is, you know, within rounding the same as the 786 that I had earlier. By the way, if I push this up a little bit, notice that there's my 78.6, right? Shift decimal point, and my current didn't change. That's because of sig fig. Okay, that's a Sears circuit. The parallel circuit, I have to do this here all the way through. See, and then I click here, and then it doesn't do it. Oh yeah, there we go. I have to click on this one here. And it takes a very long time. I have to pay attention to what I'm doing. See, there we go. And now I come up. Oh, okay. So I'm not going to put them in parallel. When I put them in parallel, it actually doesn't matter in which way I put them. Oops, one more. There we go. And then here, there. And let's see if I can get away with the same number of wires. Nope, probably not. Well, I could almost, so I use a few more wires. And now I'm going to try the same thing when I put, whoa, okay. So get the voltage down, and I put the fire out. Oh, okay, that's a little better. Here I'm going to measure the total current. By the way, you see right now here, for example, 5.41 amps. Notice when I measure here, 2.20 and 3.21, they add up to the total current, right? That is, of course, the junction rule, Kirchhoff's junction rule. Okay, so what I'm going to try here is I'm going to aim for getting 1 amp, and then I can use Ohm's law again to determine the equivalent resistance. So I'm going to drive the battery voltage down, and I get to till I get to about 1 amp. Okay, close, getting close. Whoa, okay, there we go. Ooh, I'm really close. Okay, so I have 2 volts divided by basically 1 amp, which is 2 ohms, but because I shifted the decimal point here, it's actually 20 ohms, which of course was the answer we had on the calculator, 20.3 ohms. So it still checks out. Okay, gonna give myself, well, I'm gonna look at the next problem here, and I'm gonna give myself a break. Actually, where's the next problem? I know it's there. Okay, hold up. Here's a break for me. All right, so now we're going to look at series and parallel circuits of resistors that are combined. So I'm going to scroll down a little bit. I had to actually make this somewhat larger here because these indices of 1, 2, and so on were really getting tiny. So here we have 7 resistors in this particular combination circuit, and some of these resistors are in parallel, some of these are in series. There's the oddball circuit where it's really impossible to determine. This is where Kirchhoff's rules will come in. For this particular one here, the normal, so to say, combinations of series and parallel circuits, all we have to do is combine them in series, combine them in parallel, apply Ohm's law, that kind of thing. Okay. One of the clues to analyze a circuit like that is to look at where the junctions are. For example, there's a junction here, and here we're going to look at resistor 1 and resistor 7. Yes, resistor 7 is after resistor 1, but they are not in series because there's a junction in between. So hence we ought to do something else. They already circled certain things here. I think we can see, obviously we can see that here, and it makes total sense that these 3 here are definitely in parallel with each other. There's a junction here where it splits up into 3 branches, and then it comes back together right here. The same 3 branches coming back together, which means these 3 must be in parallel with each other. So we would have to determine what the reciprocals, 1 over R2, 1 over R3, 1 over R4, plus, plus, plus. And then at these reciprocals, we come up with really small resistance, and then invert that again. Okay, these 2 are obviously also in parallel with each other. So there's a junction here, and then they come back together right here at that junction. Now, this part right here is in series with this part right here, which means, yeah, these 2 parts are in series with each other. And then when we're done with that, we're going to look at, okay, we got a junction here, we got a junction here, so all this stuff over here must be in parallel with R7. And then finally, once we have all this stuff in parallel with each other, now we can say all of this stuff here is in series with R1. Here on the side, they show us this step by step. So combine these 3 here, and then they put an RP here for equivalent just for these 3 here. Then I put an RP prime for these 2 here, and we can see, okay, so this is the same as these 3 here now after doing all the reciprocals. This is the same as these 2 here after doing the reciprocals. Then we can see, okay, these 2 must be in series, so they're simply added. They call it RP double prime. No, I'm sorry, they call it RS for series. And now that one here is definitely in parallel with this. Notice there's the junction here. It splits up into 2 branches, this one, and it comes back to the same junction. So these 2, R7 and RS, are in parallel. They call it RP2 prime. And now these 2 are combined to this one here, and now these 2 here are finally in series with each other, which means according to these diagrams, I did the same thing on the right-hand side as I did previously over here. All right, now let's go do some problems. And this is where I got disappointed in the OpenStax textbook chapter 21, because they really do not have examples for that. They have Kirchhoff examples, and I'm doing that in a different recording, but they don't have these more or less simple combination ones. So I kind of had to make one up myself. So let's look at it. Pull it up here. There it is. So this one is actually from the old textbook that I used, Cutnall, and there it happened to be chapter 20, problem 61. So an OpenStax is chapter 21, combining parallel and series circuits. So here it is. And then I put the resistances in here. Looks like when we're all done, 2 sig fig. So we have them over here. And now we're going to look at this circuit here, and we're going to say, okay, where can we definitely identify something that is definitely in parallel and definitely in series? So here's the solution. I'm going to type here. So well, where do we start? Look at R4 and R5. They're definitely in parallel with each other. So add R4 and R5 as reciprocals. Reciprocals, did I spell that right? There we go. Okay, let's see. What else? Well, notice back here, R2 and R6 are one after another. There's no junction between them, so they must be in series. So add R2 and D2. Okay, I'm just kidding. R2 and R6 in series. So these two are in series with each other, and these two were in parallel with each other. Now, these two here are in parallel with these two. So add R4 and 5, after we had combined them already, and R26 as reciprocals. There we go. By the way, if I had been a little smarter, I could have just said, okay, R2 and R6 are in series, and then all three of them are actually in parallel, R4, R5, and the combination back here. But either way works. Okay, then after I have all this stuff here, now I notice they're in series with the R1. So add R1 and R2, 4, 5, 6. I'm going to write like this, 4, 5, 2, 6 in series. And then finally, all of the stuff back here is in parallel with R3. So add, oops, I meant to keep that in blue here. Add R3 and all of the stuff behind there, 1, 4, 5, 2, 6, as reciprocals. Let me see if I still have that. Yes, I do. All right. Okay, take out the calculator. All right. I'm going to pull this up a little bit so I can fit the calculator in there. There we go. And actually, I'm going to pause if I can do this. It's somewhat better on my screen. Can't pause because I need to adjust stuff on my screen, as I said. So I'm going to clear out this from a previous problem here. Okay, so as it says here, add R4 and R5 as reciprocals. So I'm going to open the parentheses. R4 is given over here as 8.7 ohms, so 8.7 reciprocal plus R5 is given as 9.6. Parentheses, reciprocal again, so combining them I get 4.56. Notice that the smaller than the smallest one, just like it should be in parallel. And another thing that we can see is that since 8.7 and 9.6 are pretty close to each other, the result being them being in parallel is just about half of them, 4.5 compared to 8.7 and 9.6. So that's something to keep in mind when looking at these numbers. Okay, so these two were in parallel. Now R2 and R6 are in series, so it's going to be 3.5 plus 5.1. There we go. Could have done in my head. 8.6. Now that's in parallel with the 4.56. So parentheses 4.56. I'm going to give a couple more here. 3.9 parentheses plus 8.6 reciprocal parentheses reciprocal. There we go. So that's the shebang. On the right hand side are 4, 5, 2, and 6, 2.98. By the way, I could have done this here in one step less. Let me just show you. I'm going to go all the way back to the first one. This one here. And I'm going to insert here plus the 8.6 to the -1. There it is. And if I didn't make a mistake, I come up with the same 2.98. Yeah. But, well, either way worked. Okay. Now that whole thing on the right-hand side is in series with the R1. So I'm going to add 4.7. That's what it says in the problem. Enter. And now that, all of this stuff over here is in parallel with the R3. So, parentheses, the answer, the 7.68, or I can write it out, 7.68 1/6, sure, a little bit more. Plus, and what was R3? 3.5. 3.5. There we go, there we go. And take the reciprocal again and enter. So 2.40 is the answer. That is the equivalent resistance. So R equivalent equals 2.40 ohms. I'm going to fix that later here. Okay, let's look at the Fet circuit. And I'm going to prep that a little bit so that you don't watch me here doing this whole thing. Yeah, and kind of take up your time there. So I'm going to prep that first. All right, I prepped as much as I could with ch.AT, and in the process, I noticed I made a mistake. Fortunately, it's at the very end, that mistake. You might have wondered, why did I put a 3.5 here for R3 while R3 is 24.1? Well, the reason is I made a mistake. So I'm going to go back, second entry, and I'm going to put, there should not be a 3.5. Plus, let's see, second entry, plus 24.1 to the -1. So it's going to be a little bit less than 7.6. This particular resistor is relatively large compared to 7, so it should be just a little bit less than 7 when you add those as reciprocals. Sure enough, 5.8. Okay, a little bit less than that. So 5.82 should be actually the correct answer. So yeah, not the easiest thing to do that for combination of circuits. So now I'm going to go over to the ch.ET and check that out. And again, it's not going to allow me to measure resistances directly, so I have to go through Ohm's law to compute that. So let's see. And here I have to pay attention which is which. So the R3, the one that I messed up earlier, and I will adjust that voltage later here. So that's actually this one here. There we go. That's here. Then I have an R1, which is the 4.7, sitting over here. Then in the middle I have R4, which is 8.7. There we go. And an R5, which is 9.6. Here we go. So they're in parallel. And then I have an R2, which is 3.5, which I have not yet adjusted. It's a little, this part here of the ch.ET, it's a little difficult. And then I have the R6, which indeed is the 5.1. So again, when I'm all done here with this one, I should come up with the 5.82 ohms. Again, if I didn't make a mistake. So, bunch of wires here. There we go. I think those were, nah, I'm going to put the switch down here. There we go. Yep, there we go. And then this one connects here. I'm looking to my left. Well, I don't think I turned my video on anyway. So, looking to my left to make sure that I obey the circuit diagram. There we go. There. And this combines here. And I'm going to put this a little bit further down. There. And here. And here. Is that connected? I think so. Yep. And finally here. And if I compare this one here to the circuit diagram, again, if I didn't make a mistake. Now let's just give it a try. I'm going to close this one here. I'm going to take an ammeter. And let's see what I measure. Okay. I'm going to increase the voltage here. Increase or decrease. Let's see. I'm going to decrease. because then I'm aiming for 1 amp, because then I can divide nicely. There we go. All right. Oh, there it is, 1 amp. And I have 5.8 volts divided by a total current of 1 amp, which is 5.8 ohms. So in my second attempt earlier, I indeed did come up with the correct number, 5.82 ohms. Give myself a little break here before I go on. All right, next problem occurred to me as openstax threw it as the capacitances in combination as well as resistances, that I would take the same circuit and make capacitance out of the resistances with whatever values I have there in milli or microfarad, and capacitances are added as reciprocals in series, and simply add them when they're in parallel. So I'm going to scroll down here. So this is, this is the one for the resistors, and here's the one for the capacitances, and it's the same circuit, just with capacitors, and different values, of course. And unfortunately, I cannot show that in the PHET because they do have capacitors, but to actually determine what their values are when they're in combination, the equivalent is really tough. There is no such thing as Ohm's law that would tell us right away what it is. It would be more complicated to figure out. You can figure it out, but more complicated. So anyway, so the analysis of this one here is pretty similar. So here's what I'm going to do is I'm going to copy this one here. And let's see how much space I have on this. Oh yeah, just about enough space on this particular page. And of course, these here where it says R, it should say now C instead. And let me see if I labeled them correctly. I think I did. So it should all say C. I'm going to turn this off for just a moment here, or pause, so I can put the C's in there. Okay, and I think you can see what I just did. So I put the C in here for the R's. And then the other thing is that, of course, this all should be turned around here. So this one here should be in series, and then the other one should be as reciprocals. So C4 and C5 right here, they are in parallel with each other, and therefore, as capacitances, they add in series. I'm sorry, they simply add. That's what I meant. Oh, I should have done that one earlier, actually. Simply add C4 and C5. I should have done that earlier. I'll fix it in a moment. I'm going to get this one here. So add C2 and C6 because they're in series as capacitances, as reciprocals. Simply add this one here and this one here because they're in parallel as capacitances. Then C1 and all the rest here are in series, so as capacitances, they're added as reciprocals. And then finally, all the stuff here on the right-hand side is in parallel with the C3, so they simply add. And so what I should have done earlier on this one here is, instead of saying, well, add them and then series, simply add. There we go. And again, resistors are different, or just turned around, doing the opposite thing as capacitors do. All right, so I'm not doing capacitances all the time, so I'm going to see how this works out. And again, I have to adjust my screen here, because if I don't do that, then my buttons on my graphing calculators are off my screen and I cannot type. So anyway, capacitances C4 and C5 are in parallel with each other, so simply add them, which is 3.9 millifarad plus 3.7, so 7.6. C2 and C6 are in series with each other, so capacitances they add as reciprocals. So C2 is 12.6 reciprocal plus 15.5 reciprocal and reciprocal again. Enter. Okay. Now C26 and C45, they're in parallel with each other, so as capacitances, they simply add. So 6.95 plus the 7.6. Enter. 14.55. 14.55 is in series with C1, which is 11.9, so they add as reciprocals. So parentheses, 14.55 reciprocal plus 11.9 reciprocal, parentheses, reciprocal, enter. 6.54 is all the stuff on the right hand side, which is in parallel with C3, which means simply add to C3, which is 3.3. There we go. Enter. So the total is 9.84 millifarad, 9.85 millifarad. Well, actually, it's 2 sig fig anyway because of the, yeah, I can see that. So the equivalent is, what did I just say a moment ago? 9.8 millifarad. All right, and with that I'm done with the problems, but I actually will continue because I did find a few more practice ones. So I'll do that soon.